What if you could board a high-speed train and travel beneath the sea?
Travel for more than 90 kilometers and emerge on the other side in under an hour.
It sounds like something that belongs decades in the future, yet China is studying this project.
China is seriously studying a project that could make exactly that possible.
The proposal is a massive undersea railway tunnel, stretching around 120 kilometers beneath the Bohai Strait.
If built, it would become the longest undersea railway tunnel on Earth, by a huge margin. For comparison, the Channel Tunnel between the United Kingdom and France is just over 50 kilometers long. While Japan's Seikon Tunnel stretches nearly 54 kilometers, China's proposal would be more than twice the length of both.
So why is China considering such an ambitious project?
Can modern engineering really make a 120-kilometer undersea high-speed railway a reality? And if it succeeds, could this become the project that changes how high-speed rail crosses oceans in the future? To understand why China is even considering a tunnel of this scale, you first have to look at the map. The Bohai Sea may not look particularly large on a map, but it has shaped transportation in northern China for centuries.
The proposed Bohai Strait undersea tunnel would connect the city of Yantai in Shandong Province with Dalian in Liaoning Province.
Although these two coastal cities face each other across the Bohai Sea, traveling between them is far from simple.
There is no direct rail or road crossing. Instead, passengers either take a ferry, fly, or drive all the way around the Bohai Gulf.
A journey of nearly 1,400 kilometers that can take well over 14 hours, depending on traffic and weather.
Now compare that with what the tunnel could offer. A high-speed train traveling at up to 350 kilometers per hour.
That is more than just a time saver. It would completely change how people and goods move between northeastern and eastern China.
This matters because both ends of the tunnel sit in some of China's most important industrial regions.
Dalian is one of the country's largest port cities and a major center for shipbuilding, petrochemicals, advanced manufacturing. Yantai is another key coastal city with strong industries in automobiles, electronics, equipment manufacturing, and marine engineering. Every year, millions of tons of cargo move through these regions, while businesses depend on reliable transport links to reach domestic and international markets.
But this project is not only about connecting two cities. It fits into China's long-term strategy of expanding its national high-speed rail network.
Over the past 2 decades, China has built the world's largest high-speed rail system with more than 48,000 kilometers of operational lines.
As the network has expanded, attention has gradually shifted from building across plains and mountains to solving the few remaining geographic barriers. The Bohai Strait is one of the biggest of those barriers.
The idea of building a tunnel beneath the Bohai Strait is far older than many people realize. Chinese engineers first began discussing the possibility in the early 1990s, when the country's railway network looked very different from what it does today.
At that time, high-speed rail had not yet become a national priority.
Tunnel boring technology was far less advanced, and a project of this size would have been almost impossible to finance.
The idea of building a tunnel beneath the Bohai Strait is far older than many people realize.
As China's economy expanded through the late 1990s and early 2000s, the conversation started to change.
Manufacturing output grew rapidly, trade volumes increased, and coastal cities around the Bohai Sea became even more important to the national economy.
At the same time, China's railway construction entered a new phase, with thousands of kilometers of new lines being planned every year.
By the mid-2000s, several research institutes and engineering organizations had begun carrying out more detailed feasibility studies.
Different routes were examined along with possible tunnel designs, construction methods, geological conditions, and projected traffic demand.
Engineers also evaluated whether a bridge, a tunnel, or a combination of both would offer the best long-term solution.
A bridge was quickly found to have major disadvantages. The Bohai Strait supports heavy maritime traffic, including large cargo ships traveling to and from ports around the region.
Building bridge piers across one of northern China's busiest shipping routes would create operational challenges for both shipping and maintenance.
The region also experiences strong seasonal winds, sea ice during winter in some areas, and changing marine conditions.
An undersea tunnel gradually emerged as the more practical option, even though it would be far more expensive to build.
As the years passed, China's engineering capabilities continued to grow.
The country completed thousands of kilometers of mountain tunnels, expanded the world's largest high-speed rail network,
and developed increasingly powerful tunnel boring machines capable of handling difficult geology. Every major project added new experience that engineers could apply to future construction.
The project continues to receive attention, even though construction has not officially begun.
Government agencies, universities, and engineering institutes have continued studying geological surveys, tunnel alignments. These studies help answer one critical question before such a massive investment can move forward. Is a 120-kilometer undersea high-speed railway technically, economically, and operationally achievable? The answer depends not only on cost, but also on what engineers decide to build beneath the sea. And once you look at the proposed design, the sheer scale of the project becomes much easier to understand. When most people hear the word tunnel, they picture a single underground passage carrying trains from one end to the other. The Bohai Strait project would be far more complex than that. Current proposals describe a railway crossing stretching roughly 120 to 125 kilometers, depending on the final alignment. More than 90 kilometers of that distance could lie beneath the seabed, making it by far the longest undersea railway tunnel ever attempted.
It would not simply break the current record, it would more than double it.
Building a tunnel this long also means thinking beyond normal railway design.
Safety, maintenance, and emergency response become just as important as moving trains from one city to another.
One concept that has been discussed includes two separate railway tunnels, with one carrying northbound trains and the other carrying southbound trains.
Keeping trains in separate tunnels reduces operational risks and allows maintenance work to take place with less disruption. Between them, engineers could build a third service tunnel that would not carry trains at all. Instead, it would provide access for maintenance crews, emergency responders, utility lines, communication systems, and evacuation if an incident occurred.
Cross passages connecting all three tunnels could be placed every few hundred meters.
If a train ever had to stop because of a fire or another emergency, passengers could leave the railway tunnel through these passages
and enter the protected service tunnel before being transported to safety.
Similar safety systems already exist in projects such as the Channel Tunnel, but scaling them would be a completely different engineering challenge.
Ventilation would also play a major role. Unlike road tunnels filled with vehicle exhaust, an electrified high-speed railway produces no engine emissions. Even so, the tunnel would still need powerful ventilation systems to control air pressure, regulate temperature, remove smoke during emergencies.
Another challenge comes from the trains themselves.
A high-speed train traveling at 350 kilometers per hour pushes a huge volume of air through a confined tunnel. As it enters, it creates a pressure wave that races ahead like a piston moving through a cylinder.
If engineers fail to manage these pressure changes properly, passengers could experience discomfort, Equipment could suffer additional stress.
The tunnel's diameter, shape, and ventilation systems would all have to work together to keep these forces under control.
The railway itself would likely connect directly to China's existing high-speed rail network on both sides of the Bohai Sea.
That means passengers would not simply travel between Yantai and Dalian. They could board a train in cities such as Beijing
and enter the protected service tunnel before being transported to safety. The impact on travel time would be dramatic.
Today, reaching Dalian from Yantai often means taking a ferry that lasts 6 to 8 hours or driving the long route around the Bohai Gulf.
If the tunnel operates as planned, that crossing could take around 40 minutes by high-speed rail. What is currently an all-day journey could become shorter than many daily commutes. But drawing lines on paper is the easy part.
Turning this vision into reality means digging through different layers of rock beneath the sea, sealing the tunnel against enormous water pressure,
protecting it from earthquakes, and maintaining absolute precision over a long distance. That is where the real challenge begins.
If China decides to move forward with the Bohai Strait Tunnel, it won't be starting from zero. Over the past 20 years, China has carried out one of the largest infrastructure programs in modern history. One example is the Tianshan-Shengli Tunnel in Xinjiang. It stretches about 22 kilometers beneath the Tian Shan Mountains.
Engineers had to excavate through hard rock, unstable geological formations, and high-altitude terrain while working in harsh weather conditions.
China has also built hundreds of railway tunnels through the Qinling Mountains, where engineers encountered fractured rock, groundwater, and complicated fault zones. The country's experience extends far beyond tunnels. Take the Hong Kong-Zhuhai-Macau Bridge.
China has also become one of the world's leading manufacturers of tunnel boring machines. That domestic manufacturing capability provides a major advantage. Let us know your thoughts in the comments below.